Okay, this is the most difficult problem for me in the recursion course of the Udemy course I'm following. It's called grid sum. Basically, we'll be entering, as the user, a 2D array of numbers, all of them positive. That's quite important. We will be beginning from 0, 0 in our 2D array and creating a greedy robot. Basically, this works by starting from this point, 0, 0. It can either move right, down, or diagonally, and it's looking for the maximum value from those three possible choices. And once it identifies what the maximum is, it moves to that and basically adds it to our total. And it does this twice more in this instance, and we'll be returning a value of 31. It's highly recommended that you look into how directional arrays work and how a greedy robot works before you try and solve it using recursion. You can look at the multi-dimensional arrays section of this course, as far as I remember. Highly recommended. Now, let's look at how to code this specific problem. Look at the signature first. He's called it path sum, I've called it grid sum. It uses the array, a very large one. I've decided to reduce it to 10 by 10 to avoid a huge amount of memory on the stack. Then our total number of rows, total number of columns, and these last two values are actually kind of our starting position for the robot, starting from 0, 0, and basically we're going to use a direction array to calculate where the robot should go, and using the indexes from the direction array we will be changing these values. Anyway, it's a little bit more clearer if I explain it with a little bit of code. So the first step in the grid sum is to calculate a value for the sum. The first value is the top left hand corner of our 2D array, and we can find that at start row, my array, start row to start column. So that's at 0, 0 in the first time we look at the way that we're calling it. We're actually not using these last two when we're calling it from the main here. Just the total number of rows and total number of columns. And this is inevitably going to be linked to our base case. So let's have another look at here. We've got 3 rows and 3 columns, and we've got starting from 0, 0. Our base case is basically, if it's a 1 by 1 array, our base case would be when our start row, let's say the number of rows is 1 and our start row is 0. Basically, when the start row equals the number of rows minus 1 and our start column equals the number of columns minus 1 in a 1 by 1 array, that would be our base case. And the same is true for a 3 by 3 array. As you can see, we've got 3 rows and 3 columns. There we have 3 rows, 3 columns. And starting from 0, 0, our finishing point, our base case would be when the robot reaches this corner here. Not technically the base case, but that's when we're going to finish. And that is the total number of rows minus 1 is equal to our index. And total number of columns minus 1 equals our index. So for a little bit of brevity, if our total rows minus 1 equals start row and total columns minus 1 equals start column. That's when we return our sum. So in the 1 by 1 array, we've already won. If we just have a 1 by 1 array, this will be perfect. We maybe don't even need to use recursion. However, we want to be able to do this for values up to 10 by 10 arrays in this case, and that's where we're going to need to introduce our direction arrays and look at ways to increment start row and start column. So our direction array is relatively straightforward. Essentially, we want one that goes, we want a row to go down, right, and diagonally. And if you're familiar with direction arrays, this should be quite simple. Basically, this one we're going to take, to start with, from 0, 0, and then increment start row by the di here, and increment start column by the dj here, and then we're going to try and find what our maximum value is for elements at using those indices. So to do that, we're going to need values of maximum and something that records the maximum index. So we're going to go through, we've got 3 possible directions. So we're using this for loop, we're going to calculate a kind of temporary new row, and that equals our start row from here, whatever it may turn out to be, plus dii, then new column, which equals start column plus dji. One condition here, basically we don't want to go out of bounds in our 2D array, so we can't be in a position where we jump to the right here or down here. So to avoid that, we put in a condition. If our new row is greater than or equal to our total rows, really equal to, or if our new column is greater than or equal to our total columns, then we're going to continue. We're going to go look through the rest of our direction array for a different value. Otherwise, if the array value at new row, new column is greater than the maximum, remember they're all supposed to be positive and non-zero numbers. If it's greater than our maximum, then our max changes to that value. Relatively easy. And max index is also going to change to I. Speaking of I called it maxi rather than max. So far, not so straightforward, but hopefully clear and possible to follow it. Of course, I'd recommend anyone really struggling to try it themselves without using notes, and just keep repeating it until you understand it, and trace out as much as possible using pen and paper. So after we've calculated what our max is, we should really be putting this outside the loop. We've calculated our mass indices inside this for loop. Basically, we increment our start row and start column. It's either going to be going 1 to the right, 1 down, or diagonally, which is down and to the right. And basically, we're almost done. In the end, we're going to call the grid sum recursively, and return whatever our sum up here is plus grid sum, and using our array, the total rows, which isn't going to change, total columns, which also isn't going to change, and using start row and start columns, which has already changed. So let's see if this all worked, and we'll use it with a background, which is the instructor example. What would you like the dimensions of the grid to be? 3 by 3. Values are 1, 7, 8, 2, 10, 11, 20, 5 and 9, and our greedy robot gobbles up a maximum of 31 from this. Not the easiest of problems, but hopefully with a little practice the solution will be clear.